Hello, this is Professor Matt Katroulis of Rio Hondo College. This is Chapter 6 on the topic of gases in our Chemistry 110 course, Chemistry for Allied Health Majors. I first need to introduce a new concept that we haven't really discussed yet, and that is pressure. And it is critically important when we're talking about gases. And so the way it is defined mathematically is the ratio of force to area. So just like density was mass over volume, pressure is force over area. So although we will use this definition quite a bit conceptually, we're never going to actually need to use it in any calculations. How can we cause the pressure to increase? Well, we have a numerator and a denominator here, and we know that if we want to increase the pressure here, we can either increase the numerator or we can decrease the denominator. So, for example, let's say that we want to think of the kind of footwear that we could wear that would have the smallest amount of pressure. So we want to exert the least amount of pressure into the ground. Well, that would probably be something like snowshoes, because if you increase the area of your feet, of your contact with the earth, you are putting less pressure. What kind of footwear would maximize the pressure that you're putting on the ground? Well, what kind of footwear would have the absolute smallest area possible? That would probably be ice skates. Ice skates distribute your force, your weight, onto an incredibly small area, and so therefore you exert a lot of pressure on ice, and that's largely responsible for your ability to glide over the surface of the ice. Now let's look at pressure specifically from the context of a gas. When we are thinking about pressure, what we're thinking about is all of these individual collisions of gas molecules with their container. So the more collisions there are from the gas molecules, and the harder those collisions are, so the greater the force, the greater the pressure. We always want to keep that in mind later on when we're trying to rationalize why gases behave the way they do. As we go a little bit further, we're going to see other parameters, like the temperature in particular, will have a significant effect on the pressure of a gas. So the gas which is probably most familiar to all of us is air, which is in fact a mixture of several other components. We know that it exerts a lot of pressure on everything below it, and that the air goes up many, many miles above the surface of the earth. Since air has matter in it, so nitrogen, which makes up almost 80% of the air, and oxygen makes up around 20%, all of that has mass. And so we can think of the weight of the air as pushing down upon everything, including us. You could think of the same thing being true with liquid water if you're down underneath the ocean. However, with water being much more dense, the pressures that we would experience underwater is much more dramatic than what we get with air. The devices that we use for measuring pressure are called manometers, and the type that we're going to be most interested in is going to be for measuring just air pressure, and that is called a barometer. Suppose we wanted to build a simple barometer. The most effective way to do this would be to get a long, thin tube, which is closed at one end, and completely fill it with mercury. Mercury is an extremely dense liquid, and that's why we would choose it, even though it's rather toxic, over other liquids like water. You would then invert it with the closed end at the top and your gloved hand covering the bottom so that the mercury can't spill out of the tube. And then you would put that into a pool of mercury and then release your gloved hand because you don't want to get that on your skin. And owing to gravity, some of that mercury will start to fall down into the pool. But what's fascinating, of course, is that some of it will stay up in the tube. And the reason for that is that the air pressure keeps it supported. And we'll look at a picture of this in a moment. But essentially, it's the pressure of the air down on the surface of the mercury pool that keeps the mercury from falling out. And you can demonstrate this effect very easily at home just with your sink by taking a glass and filling it with water, turning it upside down under the water, and you'll see that the water stays up. It's all owing to air pressure. So let's take a look here at a very simple barometer. So as I've said, we've taken a long tube here full of mercury. Originally, the tube was completely filled. We turned it upside down and put it into the mercury, and the mercury started to fall. Now, as it's falling, gravity is pulling down on it. However, as the mercury comes out of this tube, that causes the pool's surface to rise. In order for the pool's surface to rise, it has to push back all this air. And I know that we don't tend to think of the air as exerting all this great weight upon us. It does. It exerts a substantial amount of pressure. And so eventually we reach a kind of an equilibrium here, where this mercury cannot come out any further. It cannot force back any more of the air. Now, an important value to know is that if we're near sea level on an average day, the mercury will have a height of about 760 millimeters. Incidentally, it doesn't matter how thin this tube is. It could be considerably wider, and the height would still be 760 millimeters of mercury. And it could even have a different shape. It could be more of a prism shape, and that's what the height would ultimately be. Now, what's up here? This is labeled as vacuum, meaning that there's nothing up there. There's no air up there because remember, this was originally filled with mercury. As the mercury started to come out, there's no way that air could have snuck in through the surface up to the top there. So there's nothing up here. What happens if suddenly the air pressure should start to increase owing to a weather change? Well, as the air starts to push down more and more on the surface of this pool, that will cause some of the mercury to go up into this column, and it will rise. And that's how we measure that we have a higher pressure. This column is at a higher level. Similarly, if we experience storms and the atmospheric pressure starts to decline, there's less pressure on the surface of the pool, which means that some of this mercury can start to fall out, and so this level will go lower. So, on an average day, as I mentioned before, the average height of the mercury column will be very close to 760 millimeters. What if we were at a higher altitude, so instead of being near sea level? Think about this. If you're on a mountain, you're at a higher altitude, you have less air above you. Less air above you ultimately means less pressure on the surface of the mercury pool. So some of that mercury will come out of the tube, and so we'll see that the air pressure would be, in fact, less. And so we're going to define air pressure using that value of 760 millimeters. One of the problems with pressure is that it has many, many, many units. Probably more than any of the other types of things that we want to measure. And we're going to limit ourselves mostly to 3 different units. In chemistry, we really like to use the atmosphere. It is not the SI unit of pressure, though. It is, however, very common, and it's going to be the easiest unit to deal with because what we will find here is that the air pressure on an average day is close to 1 atmosphere, keeping the numbers nice and simple. Millimeters of mercury. Now, of course, this looks like a length unit, But when we combine these together, what this is understood to mean is, what would the height be of a mercury column when we measure it in a barometer? So essentially we already saw that on an average day, a mercury column should be about 760 millimeters tall in a barometer. So we've just said here that on an average day at sea level, 1 atmosphere is the pressure, and we've also said that 760 millimeters of mercury is the pressure. So that makes it easy to have a conversion factor here, or rather an equation for a conversion factor. So an atmosphere equals 760 millimeters of mercury. That is only approximate because the temperature can change the height of that column, but it's close enough that we're not going to worry about it, and we will treat it as exact. The torr is essentially the same unit as a millimeter of mercury. However, it is an exact unit which is defined to a very specific temperature. So for our purposes, we will not treat these as being any different. You can just replace millimeter of mercury with torr. And those are the units and the conversions you need to know. There are many other units, as I mentioned a moment ago. However, you do not need to memorize these units. So the Pascal is the SI unit of pressure. It is an extremely small value, and so we usually would use kilopascals instead. Pounds per square inch should be familiar to you from your tires. Bars and millibars, which you probably have not encountered. And what we see here is that 1 atmosphere is about 101,000 pascals, which would mean it's about 101 kilopascals. It's about 14.7 pounds per square inch. And a bar is almost the same as an atmosphere. Think about this. There's 1,000 milliliters in a liter, so there's 1,000 millibars in a bar. This is very, very close. But we're going to, again, just stay with atmospheres and millimeters of mercury and torr. From here to the end of the video, we are going to focus on the gas laws, which are essentially going to be just relationships between some of the most important parameters for a gas. And these parameters are going to be pressure, which we will label as P, volume, which we will label as V, and temperature, but specifically the absolute temperature. So whenever I am talking about temperature in this chapter, I am always referring to temperature in units Kelvin. None of these laws will work in any other system of units. And in addition, we will also add to this list moles a little bit later on. But ultimately, these laws describe the relationships between each of these. So, for example, we'll look at first the relationship between pressure and volume. Then we'll look at the relationship between volume and temperature. And then pressure to temperature. So the first really important law about gases was Boyles Law. And it's going to relate pressure and volume. So let's say that we have right now a gas in a piston. And a piston is simply a container which can expand and contract, so we can adjust the volume. It's sealed, so no gas can enter or exit the container. And let's say we measure the pressure, the volume, and the temperature inside the container. Keeping the temperature the same, or we'll say constant, we decrease the volume of the container. Well, what's going to happen to the pressure in that case? Remember, you need to think about pressure in the context of molecules and particles bouncing against the walls of the container. If we decrease the volume of the container, but we're keeping the same number of molecules in there, are they going to collide more frequently or less frequently with the side of the container? And we would expect that with less volume for them to traverse, they're going to be hitting the walls more often. So as we drop the volume, we would expect the pressure to increase. And that's essentially what Boyles Law is. It tells us that pressure and volume are inversely proportional. So if one increases, the other must decrease. Another way to think of this is that if you multiply the pressure by 2, you have to do the inverse to the volume, which would be dividing. So multiplying the pressure by 2 means you have to divide the volume by 2. If you multiply the pressure by 10, you divide the volume by 10. And vice versa, if you divide the pressure by 2, in other words, you make it half, you have to multiply the volume by 2. You do the inverse. And Boyles' law only holds when the temperature remains constant. So this is the useful form of Boyles' law. The true Boyles' law form just says right here pressure and volume are inversely proportional, meaning pressure times volume is just a constant. But it's more useful when written like this. And the ones mean essentially beginning. So at the beginning of the experiment, P1 is the beginning pressure, V1 is the beginning volume, and then 2's just mean at the end. So the final pressure and the final volume. And we are assuming one more time constant temperature, and since this is a sealed container, we're also assuming a constant amount. No gas can get in or get out. So let's take a look at an example problem. So let's say we have a gas occupying 29.5 liters, and it's exerting a pressure of 640 millimeters of mercury. We're going to expand the volume, so in other words, we're increasing the volume, but keeping the temperature constant. And we want to know what the pressure of the gas will be. Well, let's go to the notes page and solve this problem. So here we are in the notes view. Let's go ahead and label the important information. So first of all, we're given the volume and the pressure at the beginning. So let's label those. So this is V1 and this is P1. If the container's volume is expanded to 40 liters, so that's the ending volume, this is V2, and we're saying the temperature is constant, so what will be the pressure? That is P2, and that is what we want to know. So what we're going to do is we will start off with Boyles' law. P1 times V1 equals P2 times V2. If P2 is the unknown, then what we need to do is get it by itself. So we can do that by dividing both sides by V2. And of course, this means that on the right side, the V2's will cancel out, and we are left with the equation P2 equals P1 times V1 over V2. You always want to solve these problems with the variables first, with the letters in there, and then you'll go ahead and insert the numbers. So let's do that. So P1 is 640 millimeters of mercury. V1 is 29.5 liters. And V2 is 40 liters. Before we solve, let's look at the units. We see that liters and liters cancel out. So the unit we'll be left with is millimeters of mercury, a pressure unit. So putting this into the calculator, we have 640 times 29.5 divided by 40. And the calculator is giving me 472 millimeters of mercury. And checking the significant digits, we see that 640 with a decimal has 3, 29.5 has 3, and 40 has 3. So we would then need this answer to have 3 significant digits, which it does. So that is the answer to the first part, which is that we wanted the pressure of the gas in millimeters of mercury. If we want it in different units, it's just a matter of doing a unit conversion problem. So if we have 472 millimeters of mercury, you'll want to recall that we said that 1 atmosphere is 760 millimeters of mercury. And we said we were going to treat that as exact. This cancels, of course, our millimeters of mercury and leaves us only with atmospheres. So taking 472 and dividing by 760 gives us 0.621. And we still have 3 significant digits, just like we did before. Charles' law is the next important gas law, and it looks at the relationship between volume and temperature. So let's say that we again have a gas in an expandable container, a piston, and we're going to keep the pressure constant, and we want to raise its temperature. So we start with a temperature and then we raise it. What's going to happen to the gas molecules? We know that when we raise the temperature of something, that gives those molecules more kinetic energy. They're going to be able to move around faster. Now, if we want to keep the pressure constant, we want to keep the collisions the same. The way to keep the number of collisions the same would be that the volume would have to increase so that the particles are hitting less often. So ultimately this gets us to Charles' law, which says that volume and temperature are directly proportional. So if one increases, the other increases by the same amount. Furthermore, pressure must remain constant throughout this whole process. So going back to that, if we double the volume, we double the temperature. If we take 1/10 of the volume, the pressure would go to 1/10 of its value. And so mathematically, we write a directly proportional law like this, where again the 1's stand for the starting values and the 2's stand for the ending values. And we have to have here a constant pressure. I want to reiterate that the temperatures must be in units Kelvin. Remember, Kelvin temperatures are always positive. We can see clearly why we can't use Celsius here. Volume is always positive. Suppose that we used a starting temperature of 50 degrees Celsius and an ending temperature of -50 degrees Celsius. Well, a positive over a positive would be a positive number, but on this side we'd have a positive divided by a negative, which would be a negative number, and you would have a positive number equals a negative number, an absurd result. So the only way this can work is if we are using Kelvin temperatures. So let's take a look at an example of this, and again I'm going to go to my notes view. So let's look at this problem here. We say that a gas is occupying 35.8 liters, and let's go ahead and label these things as we go. So 35.8 liters would be the starting volume, V1, It's at a pressure of 1.13 atmospheres and a temperature of 42.3 Celsius, which is the starting temperature. I'm skipping ahead and I see that the pressure is unchanged, so that means that I don't have to worry about the pressure. What would be the temperature of the gas in Celsius if the volume were decreased to 25 liters? That would be V2. And the unknown here is T2. Now, the first problem we have to deal with is that the temperature is not in the right set of units. So we need to get it to the right set of units. So if you'll recall, the temperature in Kelvin is equal to the temperature in Celsius plus 273. So we have here 42.3 plus 273. Which gives me 315.3, but I'm going to round the addition to the ones place, since that's where I'm limited here on this equation. If we wanted more sig digs, we could use the number 273.15 instead, but I'm not going to in this case. Now we can use Charles' law. So we have V1 over T1 equals V2 divided by T2, so long as the pressure is constant, which it is. The unknown is T2, so we need to be able to get T2 by itself. It's in the denominator, which means this is going to take a few steps. So first, let's multiply both sides by T2. That gets rid of T2 on the right side and puts it onto the left. So now I have T2 times V1 divided by T1 equals V2. The way that we want to get rid of V1 and T1 is to multiply by the reciprocal. Let me get that arrow out of the way for the time being. Make it a little smaller. So I'm going to multiply both sides by T1 over V1. And that will cause, we have T1 times T2 times V1. We're going to be able to cross out the T1s and the V1s on the left. And so this finally gives us T2, which is the only thing left on the left side, equals V2 times T1 divided by V1. Now we only have to put the values in. So V2 was 25 liters. T1 was 315 Kelvin. And V1 is 35.8 liters. We can cancel out liters. And so our units will be units of Kelvin. So in the calculator we have 25 times 315 divided by 35.8. This gives me 219.97, which I want to write out for the time being. And how many significant digits? Well, we have 3, and 3. So we need 3 significant digits here. So if we look at the 9, next door is another 9, so that has to round up to a 0, and that causes the 1 to round up. So we have 220, and we need a decimal point to keep 3 significant digits. And the units are Kelvin. So 220 Kelvin. Now we need to convert these units to Celsius, because that's what you are asked to do in the problem. And so to convert to Celsius, we essentially are going to do the opposite of what we did with Kelvin. So the temperature in Celsius is the temperature in Kelvin minus 273. So we have here 220 minus 273 gives us negative 53 degrees Celsius. Clearly, if we look again at the Boyles Law equation here, V1 over T1 equals V2 over T2, this would not have worked in Celsius because we would have had a positive number on the left and a negative number on the right. I'm going to now add to those previous 2 laws the law relating pressure and temperature, and that's going to be Geluseks Law. So let's say that we have a gas in a rigid container, so one that cannot expand, so its volume is fixed. If we heat a gas in such a container, what will happen to the pressure? Well, we've already seen that when we heat the gas, we are giving the molecules more kinetic energy. They would start to hit the walls more frequently, and since the volume can't adjust to accommodate that, they will continue to increase and increase until we stop heating the gas. So pressure and temperature are directly proportional to each other, assuming again that the volume is a constant. And again, that simply means if we double the temperature, we double the pressure. So mathematically, this is stated in a way which is fairly similar to Boyles Law, except with P1 and P2 in place of V1 and V2. I'm not going to do an example of Geluseks Law. It's very similar to what we've seen in the previous couple problems. I am going to go ahead, though, and stop this video at this point, and when we continue, we will look at how we can replace all 3 of these laws, Boyles Law, Boyles Law, and Geluseks Law, with one single law. Thank you.